welcome back everyone to the afternoon session, first afternoon session of FProPer. I hope you're all well caffeinated and wide awake. For the first talk by Troels Henriksen, and he's going to talk about actually pretty amazing work because he did a lot of footwork, I think, which is very, very useful for many of us who work in this kind of in the field of area languages by analyzing performance differences and the reason for performance differences of OpenCL, CUDA, and PIP as compilation target. So, please go ahead.
Right, thank you. So, yeah, this talk is going to be about my experiences targeting GPUs from a compiler using 3 different APIs. So I'm not going to assume too much GPU experience here, so I'm going to mention some very high-level details, and as necessary, I will explain some more details. There will be a lot of simplification here, so if you actually are a GPU expert, you may think that I am leaving out some things, and that is correct, I am. And partially that is because I am not actually, in my work, I'm not actually exploiting the full capability of GPUs. That is kind of I'm using some kind of a common denominator features, so not only am I leaving them out of my work, I'm also leaving them out of my presentation here. So just be aware of that if you are a GPU expert yourself. Okay, so how do GPUs work? The most important thing is that they don't just directly execute code the way we do with the CPU. We can't just do a few instructions on the GPU and then continue on. It's a completely separate instruction stream. Specifically, GPUs are coprocessors. They are a separate computer inside of our main computer that we send orders and data and such through various complicated APIs with the CPU itself in charge. Now, that is not strictly true. You can also just have the GPU in charge, which is the case in some weird architectures. But from most programmers' perspectives, this is how it works. And maybe you have multiple GPUs. That's not going to be my focus here. But they are coprocessors. They're not in charge. They receive orders from the CPU. They are also not directly part of the instruction set architecture or anything like that. They are just these opaque PCI Express devices somewhere on the bus. And the GPU vendors don't really document in detail how they work, and when they do, they change the details frequently. So you don't directly access them using the lowest possible level interface. You access them through various complicated software APIs that the GPU vendors provide. Some of those are pretty well known, like OpenCL, Direct3D, Vulkan, whatever. These are pretty common, and they are all for graphics. And that's not what I'm going to be talking about here. My focus is not on using GPUs for graphics. My focus is on using GPUs for computation. I think the most noble GPU is the one that doesn't even have a monitor output, because graphics, of course, are, I mean, that's not academic enough, right? Also, GPUs for compute have, of course, become very popular since, I don't know, past 18 years. And if you look at NVIDIA's stock price, it's was a pretty good idea. So GPUs are interesting because they are a very affordable way of getting a lot of compute very easily. There are more efficient architectures that are more powerful architectures, but they're also much rarer and more difficult to program. So GPUs are now and in the immediate future, and also kind of medium-term future, going to be of interest to most people who care about high performance. So the main GPU API and the first kind of real high-level general-purpose programming API was CUDA, released by NVIDIA in 2007. There were a few attempts at doing general-purpose computation using the graphics APIs before then, where you had to kind of express your computation as if it was some kind of texture operation or whatever, which some people managed to do and get good performance out of, but it was very difficult to program. But NVIDIA could see that people really wanted to use their machines, and, well, why not let them? So they made CUDA in 2007. It's completely controlled by NVIDIA, so it's proprietary, not just the software, but also the spec. So, which is great for NVIDIA, because that means when you use CUDA, your programs will only run on NVIDIA GPUs. And again, NVIDIA's stock price is a pretty good indicator of the success of that strategy. So today, CUDA is pretty dominant for various reasons. Some technical, some societal. NVIDIA also spent a lot of time donating GPUs to researchers, which was also a very excellent investment. But of course, the other companies producing GPUs and accelerators and hardware didn't really like the idea that NVIDIA controlled everything. So they came together and created OpenCL, which I think was originally by Apple, but then donated to Kronos, which has maintained it ever since. So that's an open standard, and it's still being maintained by Kronos. It has been implemented by NVIDIA, AMD, Intel, and various other people as a part of the universal standard for programming accelerators. It's not really GPU specific. I'm going to treat it as if it were GPU specific in this presentation. And I would suspect most of the users of OpenCL use it to program GPUs. But it can also be used for CPUs, FPGAs, and other weird things. It's a high-level accelerator API, they call it. It's not nearly as popular as CUDA for various reasons. One is perhaps that the API is a lot less friendly than CUDA. In CUDA, you have this combined single-source C++ dialect that is maintained by NVIDIA, where you can just mix CPU and GPU code in a pretty nice way. OpenCL is just a pure library, no language modifications, so the API is a lot more verbose, and you have to do manual online compilation and so on. So it's not nearly as popular. There's also HIP, which came out very recently. It's still developed by AMD, and is a strategic response to the fact that CUDA is controlled by NVIDIA and is used by almost all GPU software. It's essentially a re-implementation of the CUDA API, where they just did a search replace and replaced CUDA with HIP. So it's almost entirely identical, with a few improvements where they simplified some of the historical baggage in CUDA. But the idea is that you can take your CUDA software and translate it to HIP software, and then HIP is implemented both on top of AMD hardware and NVIDIA hardware, and on NVIDIA hardware just directly mapped to the corresponding CUDA operation, so it will run with no overhead. So that's the idea, a single way of programming both AMD and NVIDIA GPUs, and even provides some tools for automatically translating CUDA programs to HIP programs. I haven't evaluated that part of it, the automatic translation. AMD claims that it works great because, of course, they claim that. I have tried it a little bit, and it does actually work surprisingly well, but that's not really what I have been working on. Now, what I have been working on is that, well, we have the situation, 3 different APIs. Which one should you use for your GPU targeting compiler? There's a lot of superstition around these APIs. For example, OpenCL has this reputation for being slower than CUDA. Maybe NVIDIA's implementation is even sabotaged to be artificially slower, because of course NVIDIA, as the big evil company, wants that proprietary API to work out. There's lots of suspicion about that. Is it true? Who knows? Does HIP have any overhead compared to CUDA? Well, who knows? Which are easiest to use, and are there any real fundamental differences between these APIs? The reason why I think there are a lot of superstitions here is that it's actually really hard to have an opinion, or an informed opinion, I should say, about the differences. Because these APIs are all super low productivity. It takes forever to write anything with them. They are low-level APIs. So very few people have substantial experience in more than one of them. And of those who do have that experience, usually will only have worked on 1 or 2 programs. No one has experience writing a lot of very different programs using these APIs, or at least without their own experience changing along the way. If you start out writing a CUDA program, learn a lot of experiences, then write a corresponding OpenCL program, those programs are not going to be equivalent. They're going to be very different, probably, unless you just learn absolutely nothing in the first time around. And no one is going to then re-implement an old program just to see if there's any difference. That's not really realistic. It's very boring and it's very time-consuming. So there has been work on investigating this stuff. In particular, OpenCL versus CUDA is a very popular subject of study. But they look at just a few applications, because there are not really that many applications that are equivalent but implemented using multiple APIs. Because again, it is super boring, and it is sort of an offense to human dignity to actually do that, because it is really a waste of human time. So what I have done in this work is that, well, we're working with this compiler for Futhark, which can generate GPU code. So this is a machine wasting its time, not me. And we have implemented backends using these 3 APIs. So we do have a source of equivalent programs, because they come from the same original high-level specification, that are then turned into code using these 3 APIs in a way that is, in principle, equivalent. And I'll quantify a little bit how I mean that they are equivalent. So then the question becomes, well, how do these programs perform? We can actually look at it systematically without any real noise, because they are the same programs, just using different APIs now. So this is Futhark. It doesn't really matter as a language for this presentation. It's a high-level functional language where you can do things like map to apply a function to every element of an array. You can use reduce to combine the array to a single value, and then you can also map a parallel function over a 2D array, so it has nested parallelism. It's a pretty conventional language within this area. There's lots of similar languages and libraries, so the observations that I make here are probably going to apply for them. It's not really a very Futhark-specific presentation. The way you program parallel code in Futhark is that you use a vocabulary of parallel second-order combinators called SOACs, which again are pretty conventional. So you have your map that where you apply a function f to an element of an array. This might look different in different languages, but the concept is usually there in some way. You have a reduce, where you use an operator to reduce elements of an array. You have scan, which computes with the prefix, the reductions of the prefixes of the array. This is also sometimes called a prefix sum. And then you have some things that are a little bit more exotic, like the histogram operator here, which, can I check this? Which kind of does a reduction per index. So in this case, it says, take the value 2 and add it to whatever, to the bucket at index 1. And you see, and also here, it will add the 3 to the bucket at index 1. And you see at index 1, you have the 5 here, so that's the 2 plus 3. And here for 1, you have the 0, it goes here. So that's just a kind of, it's a special case of a certain kind of reduction, which turns out to be implementable more efficiently than if you just use the other primitives to construct it. So Futhark has a few kind of a little special constructs for performance reasons, but mostly it's a very standard kind of programming model. And then the compiler, the backend, has a recipe for turning each of these into GPU code. It's a lot like these skeleton-based libraries, where there's just a complicated recipe, where it actually looks in detail at what's going on, and it knows how to turn like a reduction into an efficient GPU reduction program. I can return a little bit to exactly how that works. So we have 3 GPU backends. The first one was OpenCL, which we developed in 2015. Then a few years later, partially based on this paranoia about whether OpenCL was maybe sabotaged or a few things that CUDA made possible that is not possible in OpenCL, which I'll return to, we made a CUDA backend 4 years later, actually done by a student. And then 4 years later, last summer, I added a HIP backend because I had an AMD GPU that I could not take proper advantage of through OpenCL, and also return to that. So we have these 3 backends. And while you might think that the OpenCL one is maybe have an unfair advantage because it's older and more mature, or maybe a disadvantage because it's older and more mature, it turns out that the way we did it is that we created a GPU abstraction layer that we came up with for ourselves. It's not really a reusable one, that the compiler really targets. And then the CPU code, the code that runs on concurrently with the GPU, is very similar, no matter which abstraction layer that you use. I should also mention that we're going to be looking at some performance results, and these performance results are what we actually observe using the real Futhark compiler, which is not a perfect compiler. It's just what we managed to construct over the past 10 years or so. So it is possible that some of the differences we see could be removed by having a perfect compiler. And I would very much suggest that someone write such a perfect compiler and then write a follow-up to my paper. That would make me very happy, especially because then I can use this perfect compiler and save a lot of time myself. So just remember, this is a kind of a practical experience report, not a kind of final theoretical answer to what are the differences between these APIs. Okay, but let's look at how they work. So these GPU APIs at the level that the Futhark compiler takes advantage of them are very similar. You need some kind of way to allocate memory on the GPU. It's a separate computer, remember? So it's a separate memory space. You can actually map it into the CPU memory space, but we'll pretend you can't. You need a way to compile GPU programs, which are called kernels, into GPU machine code. And then you need some functions for submitting work to the GPU. Call this kernel function, copy this memory somewhere, and most of these are asynchronous operations. So the program model is that a GPU kernel, a program, consists of tens of thousands of threads that are essentially running a sequential C program, plus some functions for synchronizing, if they actually want to communicate in some ways. But it is kind of a C-like language. And they're surprisingly very similar between all of CUDA, OpenCL, and HIP. So you run this kernel compiler provided by the vendor, access through the API, that turns these C programs into GPU assembly machine code, and this is typically done at runtime. You can do it ahead of time, but because GPUs vary so much in the actual machine code they use, you typically don't know which machine you're going to run on. You have to do runtime compilation, and then you can cache it and all that stuff. That also means you have a chance to specialize very late during program startup based on the specific GPU you're encountering, which can be used for good and also sometimes for evil. I won't go too much into that. The paper mentions some examples. So this is a slide full of C code, because everyone enjoys that. This is really just the prototypes for the abstraction layer that we're using. The point here is just to show that it's not very large. So there's some kind of abstract context type that contains a bunch of state. Then there's a type for GPU memory and a type for GPU kernel. And then functions for allocating memory, freeing memory, and copying memory. And we just have to implement this interface for all of the APIs. So in CUDA, in OpenCL, and in HIP. And then there's a whole bunch of initialization code, which is actually the lion's share of what the backend implementations actually look like. There's maybe 500 lines of initialization for CUDA and similar for the others, which is very bespoke to the specific backend. Then there's a few other functions, 2 more. One for getting a handle to a named GPU kernel, so a GPU function or program, and then one for launching it. And there's a bunch of parameters you provide about how many threads and so on, which are not super important, but this is just to show how small the interface actually is. So if we can implement these, 7 functions, then we can add a new backend, at least if that backend is conceptually similar enough to the existing ones we have. Okay, so then the question becomes, okay, so is there any performance difference? They do the same thing. We can run them on the same hardware, at least to some extent. So is there any difference at all? So the idea here is that we just take the same Futhark programs, compile them with the various backends, and then see how they stack up against each other on the same hardware. Specifically, I've run this on an NVIDIA A100, where I have compiled with the OpenCL and CUDA backends, and on an AMD MI100, where I have compared OpenCL and HIP. So specifically, I have not run the HIP backend on NVIDIA, even though it's supposed to work, because for reasons that are not super interesting. But HIP is not supposed to perform differently than CUDA on NVIDIA. And there are other papers that investigate that, so I've kind of left that out. So each of these benchmark programs have different workloads. I mean, you can think of them as input sets that can behave differently. And the way my metric here is that I take the average speed up over all of the workloads per benchmark, and then that characterizes the benchmark. And as we'll see, if you have a high standard deviation for a benchmark, that doesn't mean the individual runs, of course, also do more than one run per dataset. That doesn't mean that they differ a lot. It means that the different workloads have a significant difference in the speed of when comparing the two backends. It's actually a bit tricky for me to figure out how to characterize such a large data set in a way that makes sense, because every single data point is interesting, so I can't just take the average. You'll see in the next slide that it's surprisingly difficult to get a grasp of what's going on. I have 48 benchmarks, which is pretty large. It's an order of magnitude more than most papers of this kind, because no one is going to write 48 programs by hand in multiple APIs. But writing 48 Futhark programs, or asking your students to write 48 Futhark programs, that is more achievable. Okay, so these are the benchmarks. They are all from published benchmark suites. Originally, they are written in, well, one of them is Accelerate, the others are usually handwritten CUDA and OpenCL programs. And I will say that the Futhark performance is pretty close to the original performance. Some cases better, some cases worse. So these are not pathologically bad programs. They're programs that kind of behave as well as you would hope to. Okay, so let's look at what the differences are like. So this is actually a condensed form of the unreadable graph in the paper. What this shows is a speed up of OpenCL versus CUDA and HIP respectively on the two different GPUs. So higher numbers means that OpenCL runs faster than the other API. So for example, we can see that on the A100, on the n-body benchmark, on average we get a speed up of 1.43 when using OpenCL compared to when using CUDA. But you also see this huge standard deviation, which suggests that it actually varies a lot based on the data set, how much the speed up is. So we can see for some data sets it's actually slower. OpenCL is slower than CUDA, and some it's faster. So it's data set dependent, which is, of course, the worst kind of dependency. Whereas for others, I mean, the standard deviation is pretty small, which shows that the difference is not really data set dependent. And we can see that the differences range from about 40% slower with CUDA to 43% faster, and sort of similarly on the MI100. So they're all within a factor of 2, almost, except this one. So yeah, it's not a disaster, but it's not also kind of weird. So let's look at, I could leave it at that and say, yes, there are differences, but of course I didn't do that. And then I went in and did some very tedious work looking at each of these and trying to figure out what is the cause of this performance difference. So that's what I will try to give you an idea of now. And this is extremely time-consuming, because we have to look at every single program, use low-level tools to figure out what's going on, inspect its actual operational behavior, and then try to figure out why it does the way it does. So it is difficult, but in most cases I've been able to figure out why we see these differences. So one interesting difference that was a little bit depressing to discover is that by default OpenCL actually allows programs to be wrong. It allows the kernel compiler, remember the thing provided by the vendor that compiles the kernel code to the actual GPU as machine code, to incorrectly round floating point, single precision floating point numbers. Probably this is for historical reasons, because all of this is originally based on graphics, compilers, and so on. So you actually have to pass a flag to OpenCL to tell it to actually don't break my program. And this is the reason for these performance discrepancies where OpenCL outperforms CUDA and HIP. So this is why the n-body here is much, much faster, because it has a square root and such in its innermost loop. And apparently NVIDIA's OpenCL compiler is really aggressive about not doing a good job here if you don't force it to. So yeah, that was something I hadn't actually realized before I did this study. Yeah. So did I check whether they produce the same output? No, and the reason I didn't is that they are all validating. We do have a notion of correct output. But there's a tolerance to it because all of these do things like do parallel open point, floating point summations, which is not deterministic. So there's a tiny bit of tolerance, and this apparently sneaks in under that tolerance. So that's why we haven't noticed. Although in retrospect, maybe some of the mysterious failures I've seen in the past have been because of this. I don't really know. Yeah? Sort of. The reason for the tolerance is that people want to do things like sum up floating point numbers in the programs they write. And if our testing tools don't allow that, the small error that accumulates or the small variance that accumulates, then it's just really annoying to test the compiler because you end up getting false negatives all the time. So it's just a decision we made at some point to allow some tiny tolerance when comparing against the reference result, which may or may not be what you prefer. So another source of major differences is due to prefix sums or scans. And the reason is that the best known implementation or algorithm of scans on GPUs is a so-called decoupled lookback scan developed by NVIDIA researchers. And the way this scan works is that it really kind of goes against the way you program GPUs. The essence of GPUs is that you don't communicate between threads. But the decoupled lookback scan algorithm sees a GPU sort of as a concurrent machine and does communication between threads in a tricky way to avoid manifesting large intermediate results in memory. So you end up having significantly less memory traffic than the kind of standard way of implementing scans. And this works on NVIDIA hardware. Essentially, the NVIDIA researchers made this work, and then NVIDIA realized this is important, this works, so then they basically phrased their memory model such as if you do exactly this, then it is guaranteed to work. But it wasn't really supposed to work originally, and it doesn't work in OpenCL. OpenCL doesn't promise that it'll work, but even when you run OpenCL on NVIDIA hardware, it doesn't work for reasons I'm not super clear on. Maybe the NVIDIA compiler will make assumptions that are true by the OpenCL spec, or do things related to cache behavior or progress across the entire chip that are not really that this algorithm depends on. It's not really clear why it doesn't work, but I have not seen anyone being able to get the decoupled lookback scan to work on OpenCL, on either NVIDIA or AMD hardware. So when you're using the OpenCL backend, the Futhark compiler will use a less efficient scan algorithm, and that results in these performance discrepancies for programs that are very scan intensive. Now there's one interesting case here, convex hull, where the kind of inefficient scan is actually faster on the MI100. This is probably because our implementation is tuned for NVIDIA hardware. We should probably look into that. So that's one difference between the backends. Now for the next difference, I'll have to explain a little bit about the GPU execution model, which is that, yeah, GPU kernels are split into threads, but then they're further split into thread blocks, which all must have the same size, bounded by some hardware limit, usually 1024. And together the blocks form a grid. And these blocks here are what is actually sort of scheduled at a course level by the GPU. At the hardware level then, each thread block is executed by a single streaming multiprocessor, which is called something else on AMD hardware. And what is interesting is that these streaming multiprocessors, they are an actual existing piece of hardware. They're not an abstraction. Have a small bit of scratchpad memory on them called shared memory by NVIDIA. And that means with the thread blocks on a single streaming multiprocessor can communicate with each other using this small scratchpad shared memory in a very efficient manner. And some algorithms depend heavily on being able to do that. Things like reductions and scans make heavy use of it. So balancing how many thread blocks you launch and so on, and how big they are, can affect how many of them can fit on the GPU at the same time, which can affect how much concurrence you have, and so on. And this is exploited by the Futhark compiler in a kind of tricky way. So typically these are very, very small buffers, like 48 kilobytes used to be common. I think on the newest NVIDIA GPUs, you have 192 on the entire streaming multiprocessor, which has to be shared between all of the thread blocks. So the more resources you use per program, or per thread, the fewer threads you can actually have resident at the same time, which has all kinds of implications for performance. It's very tricky to balance these parameters. And we don't really do a very thorough job of investigating the best trade-off in our compiler. But we do make tricky use of it. So if you have programs that look like this, where you have an outer parallel map, and then you have some parallel stuff going on in here, there can also be a loop on top or an if or whatever, there's just some parallel function here, then one way the compiler can generate code for this is to create one thread block, not thread, per outer map, and then the threads in the thread block will collaboratively do the parallel operations in here. The big advantage of this is that all of the intermediate results here, these are scans, but they could be whatever, the intermediate result will be stored in the shared memory, this fast on-chip memory, which is much, much faster than the actual GPU memory, which by itself is actually pretty fast, but the shared memory is even faster, but very, very small. So this only works if this parallel workload in here, including the data, will actually fit on the GPU within one thread block. Otherwise, there's another way of compiling this. And actually, the compiler will generate both versions, one where it fully flattens this out and does it all in global memory, and one where it does this kind of thread block-based compilation, and then runtime, based on the observed sizes of the data, it will pick whatever it thinks will be best. Basically, it will always do the thread block version if it fits, unless you tune it otherwise. So this has an impact on OpenCL, because on AMD GPUs, OpenCL thread blocks are limited to 256 threads, whereas on NVIDIA, they are 1,024. Originally, this may have been a hardware limit, because if you use HIP to target the exact same AMD GPU, this limit doesn't exist. It's 1,024, like it has always been on NVIDIA. So the hardware is clearly capable of running larger thread blocks. And there is some fine print that applies to why this restriction may still exist. I won't go into that. It just means that if you just write a straightforward, naive OpenCL backend that just asks, well, what's the biggest thread block I can launch here, or even just try to launch one that's bigger, then you will be affected by this limit. You have to be really tricky in order to get a higher thread block size on OpenCL. And that means that some benchmarks that depend a lot on this this thread block level parallelization, they really suffer because they have to use a much slower global memory code version instead. Essentially, you get worse locality. So you can see we get these slowdowns with OpenCL compared to HIP, which is tragic because the hardware clearly supports what we need. It just doesn't expose it in the way that you would expect. Similarly, on OpenCL, you cannot query the level 2 cache size. OpenCL does specify a hardware thing you can query for called mem cache size, but it doesn't specify what that cache is supposed to be. So it's a level 1 cache in AMD, and usually it doesn't matter so much, but we have some adaptive algorithms, especially for these histograms, where we do multipassers and such based on the cache size to do some locality optimization in a complicated analytical model. And we get, this doesn't work if you don't know what the cache size is, so we'll just run slower. And if you think this, you get the level 1 cache, if you treat the level 1 cache size as a level 2 cache size, then you get very bad performance. So instead on OpenCL, on MD, we actually query for that in the runtime system. It just has a heuristic guessing at what the cache size might be. But it doesn't get it right all the time, as you can see. Similarly, OpenCL doesn't provide a way of querying how many threads are needed to fully take advantage of the GPU. So again, we have a heuristic, which is usually smaller than the correct number and has performance implications. Now, what is interesting here is also that the performance is not always worse with our guess. It's actually sometimes better, because there's no reason to think that the max capacity is actually the optimal capacity. The optimal number of threads to launch for a given GPU program, when you have a choice anyway, is pretty difficult to determine. Usually you need to use some kind of auto-tuning technique, which we don't. We just ask the hardware or make a guess, and then we run, and then this is what shows up. But the important thing here is that we cannot make the same choice on all of the backends, because OpenCL simply doesn't provide the information, so we just have to make a guess. We could, of course, make the same guess with CUDA. After all, it's just something we made up. Another cause of performance differences is what I call API overhead, because that's for some benchmarks where I can clearly see that there's a difference in how fast they perform. But when I look at the actual performance metrics, I can see no difference in the performance or in the time taken for the actual GPU operation. So the kernels, the memory copies, all of that stuff take essentially the same time. So the time is spent on something that is not measured by the GPU profiling information, which means it must be CPU side work. And since Futhark itself does very little CPU side work besides calling the APIs, these performance differences are due to the APIs themselves into having overhead. Because putting things in a queue, of course, is not free, and in some cases it is pretty costly, especially if your actual GPU workload is very small. For example, for in-body, we have a very large variance here, which is almost entirely due to a single very tiny workload with, I think, 1,000 bodies or something. That takes almost no time to run, and is almost entirely overhead. And apparently, that overhead is greater with CUDA than OpenCL on that machine. Sorry, no, other way around. It's higher with OpenCL than CUDA. That's why we see this large variance here. So for some data sets, OpenCL is much faster than in-body. And similarly here for the M100 for some of the data sets. That is, of course, not really great. Generally, OpenCL is slower, but there are exceptions. And I don't really know, maybe we're just using OpenCL in a very bad way. But I don't really see what we're doing wrong. But again, if someone writes the perfect compiler, then I can figure that out by looking at your code. Another thing is that Futhark actually does bounce checking, as you should do in a high-level language. And that's done with a pretty complicated program transformation discussed in another paper. That it's essentially based on inserting certain go-tos, so that when a thread encounters a bounce checking failure, it shouldn't just terminate itself immediately, because the GPU APIs do not provide a way for a thread to terminate execution of the kernel. A thread can terminate itself, but then if there are synchronization things like barriers inside of the kernel, you end up with undefined behavior, so that you might just deadlock the entire program, which is not a very good way of reporting an out-of-bounds error. So there's a complicated program transformation that ensures that even in the case of errors, all of the threads will just kind of wait until they get to a consistent control place in the control flow, and then they will check whether anyone failed, and if so, they will all bail out collectively. The way this is done is essentially by introducing certain go-tos to jump out of nested loops and control flow. It's kind of equivalent to returning from a function, really. This is allowed according to the specs because it doesn't induce, the way it's done is in a way that doesn't induce unstructured control flow. It only jumps forward in the execution. But the control flow is very weird compared to what normal GPU code looks like. So some of the compilers clearly choke on this kind of stuff and probably disable some of the optimizations or do a bad job at register allocation or who knows. I just see that they do a much worse job generating code when this fairly benign control flow is present, but only for some programs. It's specifically only this program, and that's the Boltzmann method, which is just got a big stencil, which for some reason just goes completely nuts when bounce checking is enabled. And interestingly, on the NVIDIA platform, OpenCL becomes much slower. OpenCL becomes slower with the bounce checking enabled, and on the AMD platform, OpenCL becomes relatively faster, meaning HIP becomes slower when bounce checking is enabled. So yeah, that is just some kind of black box compiler that doesn't like the code we generated in this specific case. And it's a little bit unclear why LBM is such just an outlier. Which leads me to the final course, which is sometimes the code is just cursed or something. There are some programs where I simply was unable to figure out why they got slower. And that's partially due to time. I could look at the disassembly for these programs and figure out what the difference is between the machine code generated by OpenCL and the machine code generated by HIP, but that's a lot of work, to put it frankly. The investigation I did do suggests that this happens for kernels that are very compute bound, and I suspect are very bounded by how many registers that they use. So if you use more registers inside of a GPU kernel, that means fewer of them can actually operationally run on the GPU at the same time. And so I suspect these are just small differences in register allocation strategies between the two compilers here that for some reason have a significant impact on performance. Like Tunnel here, for example, it's not a real program. It's taken from Accelerate. It generates very nice images. It simulates the Doctor Who intro, I think. It barely touches memory. It's just floating point arithmetic. It's super compute bound. And so this kind of performance difference is very difficult to explain. The other programs also do some kind of very fancy, very highly optimized things. These are programs that actually run really fast. So I don't really know why OpenCL and HIP behave so differently on the MI100 here. Right, a final course, which isn't really a course, but I want to mention for completeness. None of the programs I've been looked at for this paper encounter this, but OpenCL does not expose floating point atomics, although CUDA does, and so does HIP for that matter. You can simulate them using compare and swap operations, but that is, of course, slower. So if you have a program that depends on this, it will run slower with OpenCL because these operations have to be simulated. And this is a bit tragic because, again, clearly AMD's hardware is capable of doing something here, because HIP does support this, but they don't expose it in OpenCL. And I think that might actually be a limitation in the spec itself. I think OpenCL doesn't say that this is even supposed to be able to exist. All right, so the question is, can we solve this? How can we as a compiler implementer do to fix this? Well, one thing is we can pass the flag to OpenCL, telling it to actually compile the code correctly. So I've tried to do that. The other thing is that we have a lot of problems that are related to OpenCL not telling us that much about the GPU. So we can, of course just pass that information. Query it using whatever tools we want and pass in some tuning parameters to the program saying this is actually how many threads you should use, this is how big the cache is, and so on. And then at least we will make consistent choices. So I tried that, and then I get these results. So I don't know if you remember the original graph. I don't think so, but the kind of span has narrowed significantly. We still see OpenCL is a lot slower for programs that depend heavily on scans, because this doesn't solve the problem of using a different scan algorithm. But we don't have so many of these cases where OpenCL is just much faster for reasons that are not really fair, because it generates worse results. There is one interesting outlier here, which is that quicksort with OpenCL on the MI100 is much faster than with HIP. And this is interesting because quicksort is actually a scan-bound program. But the way this quicksort is written is with a really nasty scan operator that has like 8 operands, which doesn't work at all well with the decoupled lookback scan, which is some register-based locality optimization. It assumes much smaller operands. So in this case, the 2-pass classic scan is actually faster than the decoupled lookback. So probably we should teach the compiler to think a little harder about what the operator is actually doing and not use a decoupled lookback in such strange cases. All right, so this managed to narrow the gap somewhat, but there's still some really weird differences that are kind of unfortunate, despite these APIs in principle being equivalent. So my conclusions based on this work is that it's actually not difficult to target all of OpenCL, CUDA, and HIP. They are conceptually very similar, especially if you don't need any fancy features. So CUDA in particular has lots of things that we don't take advantage of in the compiler. We don't do dynamic parallelism. We don't have things like tensor calls or do warp level operations. We might want to do that. And these are mostly things that happen inside the individual GPU kernels. So we can also perhaps do it without modifying the host side abstraction layer. And with respect, it's also pretty easy to target the other related APIs as long as they have full support for computation. But performance portability remains tricky. Part of that is that the different kernel compilers have different defaults. Also, that OpenCL does not expose some hardware features, and the kernel compilers themselves are millions of lines of code. They all have LLVM with hacks inside of them, so who knows what's going on? I mean, for AMD, you can actually figure out what's going on because it's a full open source stack, but again, it's millions of lines of C++, so it's kind of, you can ask the question, but you also have to find the answer yourself. So if you only care about targeting standard NVIDIA and AMD GPUs, I would suggest that targeting OpenCL is probably not worth it, because most of the problems that we talked about here are, in some sense, OpenCL's fault. Now, with OpenCL, you can also target Intel GPUs, which you might find important. And Intel also has their own family of APIs that I haven't investigated, so maybe there's another way of doing that. So I would suggest just doing CUDA and HIP, because they're very similar, and then you can run on AMD and NVIDIA GPUs, and those are the most important ones for HPC anyway. All right? My setup is available if anyone wants to take a look, and I hope I didn't go over time.
And I think if I got it correctly, the reason that you say it's not that much work to write backends for your compiler for all these different architectures is simply that you don't use many of their features that make them different?
Partially, it's also because here you have, so if you use this abstraction layer by hand, when you wrote a program by hand, then it would probably also be easy just to switch out the implementation of the abstraction layer. But that's not how people write programs. When you sit down and write a program, you don't start by writing your own little abstraction layer. So you could have done so, but no one has actually done so. The exception is people who do things like Cocos and the other high-level libraries. In principle, they could also do studies like this. They just haven't.
So a lot of the pressure on the GPU market these days comes from people working on these very aggressive, large-scale LLM workloads, transformers and stuff like that, and various variations on those architectures, where a lot of the pressure is to try and hit the speed of light computation speed available from the hardware. And I'm curious if any of the stuff that you're working on here gets near that kind of speed of light limitation on the GPUs, and what would this look like if there was a Thunder Kittens kind of style benchmark in the middle of this?
So most of these are application-level benchmarks where it's not often clear what the speed of light might be because they are large and complicated. There are two of the benchmarks where I know we get pretty close, and that's matrix multiplication it doesn't beat cuBLAS, but it's kind of competitive. No, it's not competitive. It's slower than cuBLAS, but it's not, an order of magnitude slower. And scans, where we are close to the memory bandwidth, also for reductions and just plain maps. So all of the primitives are actually close to the peak memory bandwidth. When you need to do things like tiling, we are okay. I mean, with a factor of 2, definitely. But no, this is not. This doesn't really approach the speed of light in general. Which again, what I mean that this is kind of what you get when you write a compiler for application programming and you don't have NVIDIA level resources to spend on every single application. This is, 2 or 3 people working over years to create a compiler for a very rich language compared to what you see in machine learning.
So on your intermediate language, on your abstraction layer, I saw that you have explicit memory transfers.
Yeah.
But in particular, CUDA offers like 3 or 4 different memory models that you can use. Yeah. Have you investigated any things there? I mean, I don't think OpenCL offers that.
So by memory model, you mean things like shared virtual memory?
Well, like they have this unified memory, they have memory that is pinned or not pinned.
Yeah,
and that has all implications on the bandwidth that you can get between host and GPU. Right. It has implications on the maximum memory that you can allocate and things like that.
No, so the short answer is no, we haven't investigated, and that's partially scar tissue from our original backend, which was OpenCL. So we treated the GPU just as a completely different world. The memory is way over there, it's opaque, it's abstract. We have to manually copy back and forth, and that has become part of our abstraction layer. Now, we have actually enabled what NVIDIA calls, I think, unified memory. You can enable that, and then through our Futhark's external API, you can get one of these abstract arrays and turn it into a pointer and directly interact with it. So it works. I have observed that for the way that Futhark actually uses memory, it becomes slower. So it's not really worthwhile. And it is something that we are not really able to take advantage of within the abstraction layer as it is right now, which is unfortunate. And especially for multi-GPU applications, this will be a problem. So we will need to extend it when we start worrying about that.
Mm-hmm. Okay, thank you.
Hi, thanks for the great talk. How would things be different if Futhark supported tensor cores? And you could encode maybe some of the not obviously matrix multiplication computations as to use tensor cores. And also, would you imply that cuBLAS doesn't use tensor cores if you get comparable performance?
I don't think cuBLAS uses tensor cores, at least not for everything, because tensor cores also sacrifice performance and accuracy. And that's a very weird thing to do in a general purpose matrix multiplication. So they probably have some functions that do. If we want to use tensor cores, so that's those only really happen at the kernel level, so inside the device code that I didn't talk much about. Which means we could actually support them without modifying this abstraction layer, which is entirely about resource management. And we are actually starting work on that. So I think that will just work, but obviously it will only apply to the CUDA and HIP backends.
Any other questions? If not, then let's thank Troels again.